All right, in this video I'm going to be working some rate in and rate out calculus examples. Okay, so this is really the, very typical AP Calculus free response problem where you've got some situation, you've got rates of change, and you're asked questions about totals, really. So, a number of gallons P of pollutant in a lake changes at the rate P prime gallons per day. At T equals 0 days, there are 50 gallons of pollutant in the lake. The lake will be safe when it contains 40 gallons less of pollutant, I think. That's what they're getting at. So, is the amount of pollutant increasing at time T equals 9? This is only having a rate in. Or I guess really, I think maybe this function, or this derivative can be positive sometimes and negative other times, it looks like. Because, well, who knows? I'm not going to think about it too hard. So, how many is the amount of pollutant increasing at time T equals 9? Well, P prime of 9, I can just figure that out, is 1 minus 3 e to the negative 0.2 times the square root of 9 is 3, so that would be e to the negative 0.6. And, well, I don't know what e to the negative 0.6 is, so I'm going to need 1 minus 3 e to the 0.6. That's going to be negative 4.466. So I would say no, it is decreasing. That might give a reason. It's decreasing since P prime of 9 is less than 0. Okay. How much pollutant is in the lake at time T equals 4? Okay, at T equals 0 days, there are 50 gallons of pollutant in the lake. So P of 0 equals 50. So P of 4, we know P of 4 equals P of 0 plus the integral from 0 to 4, P prime of T dt. All right. And will the lake be safe at time T equals 6? Well, we'll find out. We've got to do this one first. P of 0 is 50 plus the integral from 0 to 4 of P prime is 1 minus 3 e to the negative 0.2 square root of t. That's kind of a lot. Okay, and I'm going to integrate that with respect to x, and 44.767 gallons. Then will the lake be safe at time T equals 6? Well, they just said if it goes under 40, it'll be safe. So I'm just going to run the exact same integral, except I'm going to change the upper bound to 6. And it's thinking, no, it is not safe. P of 6 equals P of 0 plus the integral from 0 to 6 of P prime. And we know that that came back 42.927, which is greater than 40. So, no, it will not be safe. All right, rainwater flows into a pipe at a rate of R of T cubic feet per hour. The pipe is partially blocked and only allows water out the other end at a rate of D of T cubic feet per hour. At time T equals 0, there are 30 cubic feet of water in the pipe. All right, so how many cubic feet flow in? That's the total in we would get by integrating rate in. Okay, so R of T is the rate in. And then my rate out right here is going to be D of T. I think it's always good to label which is which. Okay, so the flowed in is going to be the rate in, so the integral from 8 of R of T dt. Okay, I might, yeah, because this is kind of one of those good old-fashioned rate in and rate out problems. And so in general, I recommend on those typing the rate in into y1, sine, make sure I'm in radian mode, I am. T squared divided by 35 And in y2, I've got negative 0.04 t cubed plus 0.4 t squared plus 0.96 t. Okay, and all right, so I just need to integrate r of t, which I'd put in y1. So I'm going to integrate from 0 to 8. R of t I put in y1, respect to x, t, whatever. 76.570. Okay, is the amount of water in the pipe increasing or decreasing at time t equals 3 hours? Okay, because I suspect I'm going to need to do it again, I'm going to load y3 equals y1 minus y2. Okay, because in this scenario, what we've got here, the amount of water in the pipe increasing versus decreasing, that's just going to be like, okay, what's the rate of change of the amount of water in the pipe? And we know that the rate of change of the amount is rate in minus rate out. Okay, so R of 3 minus D of 3 is what I would get if I plugged 3 into Y3. Okay, so I'm going to call for Y3, which is the difference of R and D. I'm going to plug in time t equals 3, and I'm going to get negative 0.314. Okay, so I would say it's decreasing. You could also find the value of R of 3, find the value of D of 3, compare them, and say, well, it appears that D of 3 has to be greater than R of 3, so it's draining faster than it's flowing in. And, well, as a result, if it's draining out faster than it's flowing in, the amount of water is decreasing. We know that. Okay. At what time t is the amount of water in the pipe at a minimum? Okay, now we need to run an absolute extremum for that. Okay, so I'm going to need to make an amount function, and we weren't given an amount function, so I'm going to have to cook up my own. I'm going to say let a of t equal, okay, the starting value. Okay, that's 30. Okay, so a of t equals 30 plus the integral from 0 to t of rate in minus rate out. But I need a dummy variable, okay? Right? T is already committed to being how far I'm going to integrate, right? I can't have it be how far I'm integrating and be part of the thing that I'm integrating. That wouldn't make sense. R of x minus d of x dx. Okay, that's the function that I'm trying to maximize, right? Okay. I'm going to try to say, all right, well, I need to find the value of a of 0, a of 8, and then I'm going to say a prime of t equals, well, r minus d. It's rate in minus rate out. And I need to know where this derivative is equal to 0. Because that'll be my critical points, and that will be the other points I need to consider. I'm not going to make a t-chart because I don't have enough room here. I'm just going to list out all my critical points. I'm going to really be hoping that on the intervals 0 to 8 I've got set up right here, that I'll just only have 1 0. I just got to hope. Okay, so, and I'm going to go back and I'm going to actually turn off the graph of y1 and y2 so it just goes a little faster. That doesn't look promising. I think that's going to have multiple zeros. Please, no. Oh? All right, I feel, okay, only 1 0. That's good. And is it asking for a minimum? Yes, it is. Okay, that's a relative minimum there. It's the only critical point, so it's probably going to be the absolute minimum. Now, I don't really recommend using the only critical point method to solve these problems. I'm just going to say at t equals 3.2716584. It's not all of the digits were visible on my shot, but I recommend taking all of these, even though it is asking for a t-value and that is going to be our correct answer. I'm going to suggest that you only round in the very last step, right? And I still have more work to do, so don't round before you have before you're done doing work, right? So I'm going to say A of 3.2716584 is going to be equal to something. Okay, I don't need to write down all of this stuff with the integral, right? I can just, and also I know that A of 0 is going to be 30, because first of all, they told me, second of all, because the integral from 0 to 0 of anything is going to be 0. So A of 8, on the other hand, I'm going to need to basically, okay, I've got R minus D, that's Y3. I've got that loaded in Y3. So I'm going to go over here, and I'm going to say, I'm going to take 30, and I'm going to add in an integral from 0 to 8 of Y3, which is rate in minus rate out with respect to time, and I'll get 48.544. But we saw that the derivative, like the net rate of change, or the rate of change of the amount, it was negative the whole time, and then it went positive, and so that meant that the amount was decreasing and then it was increasing. So I know that it's decreasing from 30 to something, and then it's increasing from that to 48. We actually saw on the graph it increased for quite a while after the sign change. So what I'm going to do, I'm going to go over here. I'm going to ask for the exact same thing. I'm going to change this to 3.2716584, and I'm going to get 27.965. All right, and then I'm going to say, okay, this is clearly the lowest amount, but they asked what time t, so I would say that's the minimum. And so I would say at t equals 3.271 or 272, right, around in the last step. Okay, and a pipe can hold 50 cubic feet of water before overflowing, right? But don't solve an equation involving one or more integrals that gives the time w when the pipe will begin to overflow. Okay, so what's happening here is that the amount of water has gone over 50, has hit 50. And we want the exact time when it begins to overflow. So what we're going to say is we're going to set something equal to 50. And really what we're going to do is we're going to set A of t equal to 50. And that's part of the benefit of learning how to cook up your own total function, is that you can do some of these. Now, if you had clearly already stated let A of t equal that, you could say A of t equals 50. I would not expect to be able to import that from a previous part of the same free response question, though. I would write it fresh. And so if you're going to write it fresh, you might as well just write this. Okay, I might just write it like that. And you can use t if you want, if you're going to just call the upper bound w, and that's the thing I'm interested in solving. Then all of a sudden t is not committed anymore, and you can use it there. But if you wanted to say 0 to w of r of x minus d of x dx equals 50 when added to 30, that's cool too. All right, let's move on. Water pumped in at w liters per hour and removed at a rate of r liters per hour. Here we see this mixed media. Here on one hand, we've got an algebra equation. On the other hand, we've got a table. Okay, estimate r prime of 2, indicate units of measure. Okay, r prime of 2 is going to be approximately equal to 950 minus 1190 divided by 3 minus 1 liters per hour per hour. That's all. Use a left Riemann sum with subintervals indicated by the data in the table to estimate the total amount of water removed from the tank from t equals 0 to t equals 8. Is this an overestimate or an underestimate? I mean, I don't think there's enough information to say for sure. I'm going to say the evidence seems to indicate that r is a decreasing function. And I'm not really sure. Maybe in the original version of this question, if this was a free response question that I stole, which is really likely, they may have said, r is differentiable and decreasing. And So anyway, what was I thinking here? Oh, left 3 months sum. The total amount of water removed from the tank from 0 to 8 hours. So 0 to 8 of R of t dt. And that's going to be approximately equal to left 3 months sum. So I take the left endpoint as my height. My width was 1 there. Left endpoint is my height. Width there. Left endpoint as my height. Width of 3. Plus left endpoint is my height. So I'm 740 times 6 to 8 is a width of 2. And that is okay. Is this an overestimate or an underestimate? Well, I'm using a left Riemann sum on a decreasing function, so that feels like an overestimate to me. So I'm just going to assume that this is decreasing for the purposes of this problem. Okay. And you could say R of t is decreasing, especially if you don't have any evidence and it's like it looks like it's going down. But if you knew that its derivative was negative, that would probably be a better response for AP calculus, right? Because we want our explanations to be in terms of derivatives and signs, positives, negatives. Okay. Use your answer from part B to find an estimate of the total amount of water in the tank to the nearest liter at the end of 8 hours. Okay, so we started off like, okay, so the amount of water. Okay. Saying that A of 0 is 50,000. So A of 8 is equal to 50,000 plus the integral from 0 to 8 of rate n minus rate out. But maybe I'll write this as two separate integrals right now, because it wouldn't really make on one hand once you have to use Riemann sum for the other one. We're going to bring that guy back. Okay, so I want 50,000 plus, you can't see the function, but I'm going to integrate that w of t right there from 0 to 8. Maybe I'll just leave that there. Plus math 9 on 0 to 8 of w, I didn't type that in or anything, 2000 e to the negative t squared divided by 20. Okay, whatever. And, okay, I've got that. But then I still check that integral that I approximated using the Riemann sum. Now what I'm going to do is I'm going to actually use the calculator, and I'm going to say minus, and then I'll start in a parentheses, so I'll just type in what I see, 1340 plus 1190 times 2 plus 950 times 3 plus 740 times 2. And if if my lack of parentheses makes you uncomfortable, then you can use more parentheses, but I'm confident I know how the calculator works in terms of order of operations, so I'm good. And I'm going to say to the nearest liter, that will be 49,786 liters. 49,786. Cool. All right. No calculator. Water is pumped into a tank at a constant rate of 8 gallons per minute. Okay, so rate n 8 equals 8. Okay, water leaks out, rate out equals square root of t plus 1. Oh, that's clever, because we know that the square root of 121 is 11. At time t equals 0, the tank contains 30 gallons of water. How many gallons leak out of the tank from time? Okay, so we want to integrate rate out from 0 to 3. 0 to 3 of t plus 1 to the 1/2 power with respect to t. That's going to be, okay, you can use the substitution on t plus 1, but then du would equal dt, and it's like, oh, why would you do that? Okay, so what we're going to do is we're just going to add 1 to the power. That's 3/2, and then divide by the new power. That's 2/3. And I might recommend you try to take the derivative of this, with chain rule and everything, just to make sure that you believe that that's a valid antiderivative. but it is. And I'm going to go from 0 to 3. Okay, so this is 2/3 of 3 plus 1 is 4 to the 3/2 minus 2/3 of 1 to the 3/2. Okay. Now, in a free response setting, this would be a safe place for you to stop, but I could easily see this being a multiple choice no calculator problem where you had to actually evaluate 2/3 of 4 to the 3/2 and 2/3 of 1 to the 3/2. So I'm going to do that just to make sure that you would know how to if you had to. So this is 2/3. 4 to the 3/2 is I take the square root of 4, and that's 2, and then I take that to the 3rd power. So that's going to be 2 to the 3rd is 8. Okay. I'm going to factor out the 2/3 and say it's 2/3 of 8 minus 1. So that's going to be 14/3, right? Because it's 2/3 of 7. All right. How many gallons of water are in the tank at time t equals 3 minutes? Well, the amount of water at t equals 3 would be, well, the amount that we started with, 30, plus rate in is 8, so 8 times 3, minus 14/3, right? Because it's the starting amount plus the integral of rate in minus rate out. But in this situation, we just did the work for the total out. Total in is just multiplication if rate in is constant. So we don't need to actually integrate, even though that is what we were doing. We were finding areas under curves. We just weren't thinking about it like that. Okay. Write an expression for the amount of gallons of water in the tank at time t. Okay. A of t, it starts off with 30 in it. Okay. Plus, and pumped in at 8 gallons per minute. So 30 plus 8t minus the integral from 0 to t of square root of, t is already committed, so I'm going to say x plus 1 dx. Okay. Another way I'm realizing that, another way you could have written this, maybe I'll write it in orange, is I could be plus, just to go back to what we had said, the amount is the initial condition plus the integral from the time that you get the initial condition from up to t of rate in minus rate out. Right, and that would end up being the same thing. Okay. With kind of this whole thing as my integrand rather than just the x plus 1 square root. All right, at what time t is the amount of water in the tank at a maximum? Okay, another absolute maximum. And let me see. This is... Yeah, I'm going to switch this because I know there's another solve for the time problem. I'm going to say, what is the maximum amount of water? Find the max. Find the maximum amount of water. Find the maximum value of A of t. So I'm going to do a different problem than this says, and I'm just asking for freedom because there's another, we've already done one where we've solved for the time value. There was one where we solved for the time value in the lesson when I delivered the lecture to you in person. And then there's one later in this homework set, so I'm just going to go with this. Okay. Maximum value of A of t on 0 to 120. Well, I need to consider 0 and 120, but also any time when A of t equals, or A prime of t equals 0. Okay, A prime of t equals 8 minus the square root of t plus 1. And I might be interested in where that's equal to 0. Okay, this is definitely the type of equation we need to be able to solve in this class. So that's 8 equals the square root of t plus 1. And we're going to square both sides. Now, one thing that I will tell you about, we know that there's something we need to remember when we take the square root of both sides of an equation. There's actually also something that we need to remember when we square both sides of an equation, and that's we need to check the solutions for extraneous solutions, because what can happen is you can have two things that are not equal, like 4 and negative 4, and then you would square them and they would look equal. Okay, that's why you have to be careful about squaring both sides of an equation. So that's going to be t equals 63. All right, and then I'm going to actually say, okay, well, at time t equals 0, there are 0 gallons of water. Okay. Oh, wait, no, that's not true at all. There are 30 gallons of water. Okay, then I'm going to need some more paper to actually make these computations, figure out the amount of water in the tank at time t equals 63 and at time t equals 120. Right, so I'm going to, I've got my function up there, and I think this one looks a little easier for me to work with right here, so I can do that. So it'll be 30 plus 8 times 120. You just think, this is arithmetic, it's just got that extra 0 on it. 12 times 8 is 96. Okay, we are expected to know our times tables up to 12 times 12. 12 times 8 is 96, so that's 960. Minus the integral from 0 to 120 of x plus 1 square root dx. Okay, equals 990 minus, okay, we know that that's from the integration that we did before up here. The antiderivative is 2/3 t plus 1 to the 3/2. As x is going to run from 0 to 120. And then what's going to happen here? Okay, 2/3 of 121 to the 3/2. Oh my. Well, that'll be 11 cubed. And that's a big number, and you're not supposed to know that. So I'm going to just hold on to it. And I might also factor out that, because then when I run 63 through here, I'll be able to just compare the numbers that are on the inside, if that makes sense. So 990 minus 2/3 of 121 to the 3/2. I take the square root of 121, I get 11. You cube 11, I don't know what happens, but I'm committed to not using a calculator. Minus 0 plus 1 is 1 to the 3/2 is 1. Okay, that's the amount at 120. So 990 minus 2/3 of 11 cubed minus 1. Okay. Now I need to do the same thing, but for t equals 63. So a of 63 is going to be equal to 30. 8 times 60 is 480, plus 24 is going to be 504. Minus, okay, I know the antiderivative is 2/3 of x plus 1 to the 3/2 as we let x run from 0 to 63. And this is going to be 534 minus 2/3 of, all right, hold on, why am I tripping on this? Oh, yeah, I take the square root of 64, that's 8. I take that to the 3rd power, 8 to the 3rd, minus you plug in 0 and you get 1 to the 3rd. Okay. I don't even know 8 to the 3rd, although I could probably take a guess. I think it's going to be 2 to the 9, which is 512. That kind of makes sense. All right, I'll copy that in. 534 minus 2/3 of 8 cubed minus 1. I don't know how I'm supposed to know how to do this one without a calculator. Let me think about this. Oh, whoops. I was back here, and I got a phone call, and I was trying to think about what I'm supposed to do with that. I don't know. I don't see the arithmetic thing. I don't know if maybe this was I have a feeling if this was a AP Calculus free response problem, it might have been from like 1993 or 1994 when you were, or maybe 83 and 84, I think. Both, like, there was 2 different times where you were allowed a scientific calculator. And this would make sense, right? Because all of the integration we can do by hand. It's just that last step. I don't know what to make of this. So what I'm going to do is I'm going to bring in a scientific calculator. All right? And we're going to run these numbers. So 990 minus, and this one's even got a fraction bar, 2/3. No, whoops, that didn't. 2/3 of 11 to the third minus 1. 310 divided by 3. Okay. So maybe I could actually get into a decimal and get 103.333. Yeah, this feels right. This feels like this is what you were supposed to do at the very end, just to check the numbers. 534 minus 2/3 of 8 to the third. Yeah, because 11 to the third and 8 to the third both are... No, 8 to the third is not outside of the realm of arithmetic you're expected to know in Cal BC. You're supposed to know powers of 2 up to 1024, I believe. So 193, that's going to be the maximum. Maybe you were supposed to say that this was the only interior critical point and it was a relative maximum, therefore it was the absolute maximum. But I personally don't prefer that technique because it's very touchy on the free response scoring. Okay, so 193.333. So I would say that the maximum amount of water is that 193 gallons. Which, again, in case you're just now starting to watch or forgot or whatever, I know that that's not what the problem had asked for in the first place. It was asking for the time, the t value that gave us that absolute maximum. I don't really care about that. I decided to go get the actual amount because there's another one that's going to ask for the value of the independent variable that gives you the maximum. So, number 5. For 0 to 31, the rate of change in the number of mosquitoes in your yard is given by R of t as 5 root t cosine t divided by 5 mosquitoes per day. All right. So this is just one rate of change. There are 1,000 mosquitoes at t equals 0. Sounds nightmarish. Okay. Luckily, it's getting to be winter time, and there's not so many mosquitoes outside. So show that the number of mosquitoes is increasing at time t equals 6. Well, that would be R of 6 equals 5 root 6 cosine of 6 divided by 5. What this is equivalent to showing is that, well, yeah. So cosine of 6/5 is 5 square root of 6 cosine of 1.2, right? Cosine is positive from 0 up to pi over 2, right, where the x-coordinate is positive. And pi over 2 happens to be bigger than 1.5 because pi is bigger than 3. So I'm going to say that this is all greater than 0. Okay, I don't even need to use a calculator for that. At time t equals 6 is the number of mosquitoes increasing at an increasing rate or increasing at a decreasing rate. It's a good one. Okay, so R is the rate. So if we want to know if, we just showed it was increasing. If we want to know if the rate is increasing or decreasing, we take the derivative of the rate. So I'm going to take R and I'm going to take its derivative and I'm going to plug in 6. Okay. I think I'm going to plug in, and I'll probably leave y1 minus y2. Yeah, whatever. R prime of t, or R of t is 5 square root t cosine. Make sure I'm in radian mode when you hit cosine of t divided by 5. Okay. Then let's see, math 8 to get the derivative with respect to time of y1 at t equals 6, negative 1.913. And how many mosquitoes will be, so it's increasing at a decreasing rate because R is the rate and R's derivative is negative, so, okay. how many mosquitoes in the yard at time t equals 31? The amount at 31 would be 1,000 plus the integral from 0 to 31 of r of t dt. Okay. 1,000 plus the integral from 0 to 31 of y1 with respect to time. $964.335. Okay, that's the number of mosquitoes. Okay, if we rounded to the whole mosquito, that would be 964 mosquitoes. Man, not a good month for, pest control. Right? We started with 1,000, ended with 965. Basically no difference in number of mosquitoes. It's a massive number of mosquitoes. So the nearest whole number, what is the minimum number of mosquitoes between 0 and 31? Well, I know this is convenient because okay, my endpoints, I've already got those. So at t equals 0, I've got 1,000 mosquitoes. At t equals 31, I got 964 mosquitoes. All right, I'm going to need to define n of t, and I just don't see any world where this is enough room, but n of t, number of mosquitoes, is equal to 1,000 plus the integral from 0 to t of r of x dx. Okay. And so I just need to find where is n prime. I need to write a formula down for n prime. Okay, we know how to take the derivative of these functions defined by integrals. It's going to be r of t. We know that. And we want to know where that's equal to 0. Okay, so we're going to have to graph it on 0 to 31. So 0 to 31, we're going to graph r of t and not y1 minus y2. And okay, it went negative for quite a while, and I don't know. Okay. All right, now calculating a 0 that's, I don't know, goes from 0 to 31. Maybe it's from between 5 and 10, we'll say. Okay, perfect. We're finding one of them. 7853. Okay, to the nearest whole mosquito. I don't think we have to worry so much about round-off error on this one, so maybe I'll copy like 4 or 5 decimal places. Okay, this is a relative maximum. Okay, and so we're not interested in it, but on the free response section of the AP exam, your options are either just like pretend like it's a candidate and run it through, or pretty much risk losing the point, because the process you have to go through to exclude that one from consideration is pretty arduous. You have to say that you have to justify the fact that it's a relative maximum, so you have to say that R goes from positive to negative. And you also have to say that a relative maximum is not a candidate for an absolute minimum, which I think is just not realistic for us. So we're just going to pretend like it's a candidate. So 7.85398. Right, and we'll do that. And then I'm going to calculate the other 0. It's between 15 and, say, 30. And I get 23.56194. 56194. Okay, cool. And now we're going to run these through n of t. Okay. Now what I'm going to do is I'm going to let y2 equal 1,000 plus math 9 on 0 up to... Actually, I'm not, because I only need to do this twice. If I need to do it more than twice, my advice to students is to never put an integral into y equals, because it just like really jams up the calculator. It takes a long time. It can do stuff, but it's not the thing to do. So it's never the thing to do, is what I'm saying. So I'm going to say 1,000, because we can always just like copy what we had entered in the calculator before and just change the number, plus math 9, 0 up to 7.85398 of y1. It's thinking. Okay, 1,039 mosquitoes. We knew that was a relative maximum. So, odds are pretty good. It was not going to be a absolute minimum. I'm going to copy the same thing down, and then we're going to do 23.56194. That's 842. That's going to be my absolute minimum number of mosquitoes, so 842. Okay, I wasn't going to be able to fit the word mosquitoes into where I had room for it, so we're with bugs. Write but don't solve an equation that would give the time x at which mosquitoes are extinct from your yard. Okay, so let me think. Oh, I see how that's going to go. Would eventually happen. So we want the number to equal 0. We've already got that again. That's why I like having the total function, right? It's because we can just say, okay, 1,000 plus the integral from 0 to the special time x, and then we can go back to r of t dt. You add that together, and you get 0 mosquitoes. That's extinction. So that would be the write and don't solve an equation involving an integral. Okay. The first snow of the year started falling at midnight. From midnight to 9 a.m., snow accumulates on the driveway at a rate of f of t cubic feet per hour. Okay, where t is measured in hours since midnight. I think since it's the first snow of the season, it's going to be at t equals 0. There's no snow on the driveway. Okay, so how many cubic feet of snow have accumulated on the driveway? That's going to be the integral from 0 to 6 of f of t dt. And now I'm going to need to use this, so I'm going to have 7t e to the cosine t. Okay, that's cool. And hold on, what am I? Oh, yeah, integrating from 0 up to 6. y1 with respect to time, 142.275. Okay. Find the rate of change of the volume of the snow on the driveway at 8 a.m. Okay. Well, the rate of change of the volume would be like the rate in minus the rate out. So that's going to be R of... All right, yeah, not sure what I was going to do with that R there. I kind of lost my place. It's been a few minutes. But if I want the rate of change of the volume of the snow, then I'm just going to take rate in minus rate out, right? So at time t equals 8, f of 8 minus g of 8 is going to be like my net rate of change, right? The rate in minus rate out. F is the amount of snow that's falling. G is the rate of removal. So f of 8 is going to be 7 times 8 is 56. E to the cosine 8 minus g of 8 is right there, 108. Okay, that's going to be the rate of change of the volume of the snow at 8 a.m. Okay, and I'm not really sure what I was going to be doing with that, but it's all right. So let h represent the number of cubic feet of snow Janet has removed from the driveway at time t. Write a piecewise defined function for h with domain 0 to 9. This one, I worked this problem in the lesson with a couple of the sections of my class. And this one, you just kind of have to be a little creative. I don't really know what else to say besides, okay, h of t is going to be, all right, the first part of it's going to be easy because she's not out there removing snow until t equals 6. So where t is less than 6, I'm going to say, well, the amount of snow removed is 0 because she hadn't even started. And then it's going to be 125, and you would think it would be like 125t, right? But then it has to be 0 when t equals 6. So what I'm going to do is I'm going to say t minus 6, right? So for 6 is less than t is less than 7. Right? And then, you know, as far as the less than or equal to, I don't think we're really going to worry about that too much. Then past that, okay, you would think 108 times t minus 7, right? But if you plugged in t equals, say, 7.5, it would say that she had removed 54 cubic feet of snow. But we know that's not realistic because we know that she's already removed 125 for that, 6 a.m. to 7 a.m. hour. So that's where we're going to have to add in 125, and then that will be 7 to 9. Okay, or, up to the inequalities or whatever. Okay, that's h of t. That's probably not something that you will ever have to do again. Cook up an antiderivative of a piecewise constant function. Basically, yeah, we don't have to do that. But it's okay. So, or really, yeah, like, that was a weird one. Okay, I'm sure that the year that this was on the AP exam free response, this was the problem that they were talking about when they came out of the exam. And, they were asking each other about it on the internet, whatever. So how many cubic feet of snow are on the driveway at 9 a.m.? Okay, so there's none on the driveway when it starts snowing. So the amount in is going to be the integral from 0 to 9 of f of t dt. And that's going to be, well, let's find out. The integral from 0 up to 9 of 7t e to the cosine t dt. And I get 367. All right, and then the integral of g of t from, say, 0 to 9 is going to equal 125 plus 2 108s. Okay, I need to subtract these. Okay, so that's 216 and 125. Just don't want to be wrong. That's 341. And I'm going to take 367. In fact, well, I'll show you what I'm doing here. I'm going to take 367 and some minus 341. I'll say there's 26.335. Okay, if this was actually an exam or something, I would probably be a little more explicit about the fact that I was subtracting these, but this is all I'm going to be able to record in this sitting, and there will be a second part for that last page. So thanks for watching so far. I'm probably showing you right now where to click to get to the part 2 video.